Hi there, fellow experimenter. My name is John. This lab will attempt to determine the mass of a remote black hole based upon time-stamped positions of a star that is orbiting the black hole. To determine the mass of the black hole, Newton's universal gravitation law will be used. This states that for any two objects in the universe that have masses m1 and m2 and whose displacement is r, the force on m2 due to m1 is given by this wonderful equation. Consequently, to determine the mass of m1, we must evaluate this equation. The crucial part of this relationship is to determine the force on m2 by m1. The force on an object that causes it to orbit can be determined from the momentum principle. If a small enough a distance increment around the orbit is taken, where the force is nearly constant, then the force may be calculated from orbit velocities. The velocities in orbit can be determined from the displacements over small time intervals. The system we will consider is a star rotating around a black hole. The gravitational force exerted by the black hole will be assumed to be the sole external force acting on the star. The position data of the star relative to a fixed origin is in stardata.cvs. A small example of the plots are shown in the table. All the values are in meters. Of the plot of this data is shown in green, with the interplot time being 1 day. The black hole position is shown by a cross. The curve seems to form an ellipse, with the black hole as one of its foci. We will now look at how the physics are modeled in VPython. The VPython program has the following broad sections described in this slide. The visualization of the motion of the star around the black hole is configured as in the Python script. The star is the yellow circle and the black hole a black circle. The origin is marked in green. The net force is colored yellow, perpendicular force blue, and the parallel force black. The arrows are scaled according to their magnitude. The system properties are configured by this Python segment. Newton's universal gravitation constant is specified. The mass of the star is specified along with the black hole position. For each plot point, the mass of the star will be written to a CSV file for further analysis. To calculate the velocity of the star, we need first to read the position data at each plot time. For each pair of plots, the velocity components in the x and y directions are calculated and stored. The main calculation loop computes the net force exerted by the black hole on the star. The calculation takes a pair of velocities and computes the change in momentum over the plot interval. That's this point here, and there is the change in momentum. This gives the rate of change of momentum and hence the net force there, and the rate of change is computed there. Calculation of the parallel component of the force is performed by this section of code here and assigned to FNet parallel there. Calculation of the perpendicular component is by this expression here and assigned to the perpendicular FNet there. The main computation for the black hole mass is provided by this expression here. It is written to a CVS file for later processing. We will now run the program. As we can see, the orbit seems to be an elliptical one, and the yellow force, the FNet force, is quite substantial and points towards the black hole. The calculated mass of the black hole is stored in a CVS file. The mass is calculated for each plot point on the orbit. The results of running the Python script and accumulating 1093 samples of the black hole mass resulted in a mass of 2.377 e to the 31 kilos. The force Fnet caused by the black hole is the external force on the system that causes the star to change its behavior. The cause in this case is gravitational force and causes the momentum of the star to change. Forces parallel to the motion cause speed change. Forces perpendicular to the motion causes direction change. If the black hole is replaced by one with identical motion properties, then there is no way to tell the difference between the two black holes, and they must have the same masses. The equation shows the dependencies, and since the force, distance, and mass of the stars are all the same, the black hole must be the same size.